The previous video stopped here, so I will be continuing from here. Describe gives you these descriptive statistics for the data frame which contains the midterm grades from part 1 last semester. So there were 36 students in the class, the mean was 43.44, and the other statistics are shown here. So next we move on to perform bootstrapping, which is basically sampling with replacement. So there is a sample function in pandas, because this is a pandas data frame. So we're sampling with replacement. So replace equals true. If you make replace equals false, then you're not sampling with replacement, and you will basically be shuffling the entries, the 36 items in that column. So what we want is sampling with replacement. That is what bootstrapping is all about. How many samples? What's the sample size? 36. That's what is shown here. So this gives you one sample size, meaning one bootstrap sample with 36 items. And now we can get the descriptive statistics on that. And you will see the mean is different from the mean of the true data set. Mean of true data set is 43.44. This is just one realization. And if we keep running this several times, the mean keeps changing. And like I showed in the Excel spreadsheet, you will generate multiple of those and we can calculate the mean of each of those bootstrap samples. Here I'm just showing you the result before using the describe function on it. And that shows you, if you look closely, you will be able to find some repeated indices, right? So 28 index is repeated. So the 28th student shows up a couple times here. You had the score of 48 is also showed here, which is what you get from sampling with replacement. Same deal here with the 27th student. If you make it equal to false, which you shouldn't do if you're trying to do bootstrapping, then no student is repeated. So you basically shuffled it. You used to go from 0 through 35 to get 36 students, and now it's just shuffling it. So it's the order has changed, but the entry remains the same. So if you were to find the average on this, it will be identical to the original average because it's the same scores in there. So if you use describe on this, so it's identical to the original average, which means it just shuffled it. So that's what is important to note. Bootstrapping is all about sampling with replacement. So this guy has to be set to true. Good. And that summarizes what I explained earlier. The next step is to get the mean for several bootstrap samples. This is just one bootstrap sample, right? So we want to get 1,000 bootstrap samples. That's what this is doing, 1,000. Then we don't want to store all of those 36 samples, right? 1,000 times. We want to get the average of each of those 1,000 realizations and store that into a data frame called Bootstrap. It's going to have only one column titled mean grade, and it's basically the mean of the 1,000 bootstrap samples we generated, each with a length of 36. And when we run this, now bootstrap contains 1,000 means, 1,000 bootstrap means. And once we have those kinds of data sets, we know what the deal is, right? We're going to plot a histogram using the data. And that's precisely what is being done here. So plot function kind equals hist. We did all of these in topic 6. And When you run that, you obtain this histogram. The original data set looked like this, but when we generated 1,000 bootstrap samples from this distribution and calculated the mean of each of those, we plotted it up and got this, which looks almost symmetrical. If you change the number of beans here, the appearance can change a little bit, right? Beans equals 30, for instance. Then it looks a little different. We can plot the vertical line at the mean. So the mean is about 43.44, which is basically almost identical to the mean of the original sample containing 36 results. Next, we can also show the 2.5th percentile and 97.5th percentile, which is basically the confidence interval as discussed in the previous video. So confidence interval ranges from 41.49 to 45, and this will be the result if you were going to estimate the average performance of any group of second year PETI students taking this course. So the expected average will lie within this interval. I haven't calculated what the average is for your midterm, but I'm pretty sure it's going to be within this interval, within a 95% confidence. So that's how you use confidence interval. Now we move on to something slightly different, but is also interesting considering the current pandemics we're facing. So in 1854 in central London, there was a deadly epidemic of cholera. And a physician by name John Snow used statistics and some elegant plotting to figure out the origin of the cholera. And I believe this probably led to the solution of the problem they were facing back then. The topic again is hypothesis testing, which means testing hypothesis. So we don't jump to conclusions, right? Most of the times what we call conclusions are basically hypotheses and they need to be tested. And we use inferential statistics to test hypotheses. And that's what we're going to do right now. We're basically repeating what John Snow did back in 1854. The data set we need is already uploaded in GitHub. It's data for the pumps serving the region around central London, and also the number of deaths due to cholera also recorded. So that's in cholera.csv. We're trying to figure out whether it's a particular pump being responsible for the deaths. So the pump data is pretty straightforward. There are 8 pumps serving the entire city. The longitude and latitude location of each of the pumps are provided here. We don't want to work with the longitude and latitude locations directly, so we make one of them, pump 0, the reference point, so that will be in the center. Then we subtract out the latitude and longitude location of each of the other pumps from the reference longitude and latitude. And of course, for the reference, it's going to be 0, and the others are all relative to that. So that's the data for the pumps. The data for the deaths due to cholera are given here. They also have longitude and latitude. XY, again, will be normalized relative to that of pump 0. So you're subtracting these two values from that of the reference location, which is the location of pump 0. So you have that, and you can also plot these on the same graph. So you can scatter plot these points, 8 points, with a particular color, and scatter plot these 240 points with another color. Here we're not showing all of the 240. We're using our knowledge of indexing. So start out with the first item, no second value, which should have been stopped, meaning go up through to the end, then go in increments of 20, which is why it's showing 0, 20 until it gets to the last. So this is how you can see most of the data set without displaying everything, because it's going to fill up the entire window, which we don't want. So we plot up those two data sets using scatterplots, like I said. That's the PLT, which is from matplotlib.pyplot scatter data x and y, which are the coordinates, of course, relative to the location of pump 0, and pump 0 will be at 0, 0, which is right here at the center. So the pumps are in the blue, the red dots are the location of the deaths recorded. We can also load a map of London and overlay these on the map so you can see where all these points correspond to. And we import the map of central London here and still plot up the scatter plot over it. And this is what it looks like. So you can see the deaths line up along the streets, which is where people live. What do you observe from this? Because we're trying to figure out the source of the cholera outbreak. Are the red dots centered around certain pumps? Yes, the red dots surround pump 0. So can we conclude that pump 0 is responsible for the cholera deaths? So we don't call that a conclusion, right? It is a hypothesis. And we're going to test the hypothesis that pump 0 is responsible for the deaths. That's what John Snow did using statistics. First thing we're going to do is to count the deaths closest to certain pumps. So I go back up here to the cholera death data. There is this last column here, which is closest pump. First column of data is the number of deaths. So there were 3 deaths at this location, and the closest pump to that location was pump 0. There were 2 deaths at this location. Closest pump to that point is pump 1. And to figure out the number of deaths closest to, say, pump 0, we're going to have to figure out all the zeros here and add up the number of deaths corresponding to those. So there is 0 on row 0, 0 on row 3, row 4. So you're going to add 3 to 1 to 1 to 1 to 1 to 1 and to 3, because those are the death locations which are closest to pump 0. And that's what we're going to do next. We want to count the number of deaths closest to each of the pumps. And that's what we obtain from this. So cholera closest, then count the number of values. Actually, this is not the final result. So this is only counting the number of times pump 0 shows up in this data set, the number of times pump 0 shows up. But the number of times pump 0 shows up is not the total number of deaths, right? That's important to be cognizant of. So first thing I do is to show the number of times the pumps show up. So 171, but it doesn't mean 171 people died due to cholera. To get the number of people that actually died, you're going to use group by. So first group the data by the pump they're closest to. So you will grab all the 171 closest to pump 0, then you will add the entries in the depth column using the sum function. And that's what gives you 340. So 340 people died due to cholera closest to pump 0, 65 died closest to pump 1, and on. And again, our focus is to test the hypothesis that the deaths surrounding the region of central London is due to pump 0 delivering contaminated water. So that's what we're going to have to test. So how do we test the hypothesis? That's what leads us to null hypothesis. So null hypothesis, which is documented in the next section, I believe, is all about an alternative explanation instead of the hypothesis we have. So for binary cases like the election between Ed Orgeron and Nick Saban, the hypothetical election we discussed, it's either Saban wins or Orgeron wins. So if the hypothesis is that Saban will win, the null hypothesis is that Saban will not win, which basically means he either loses or ties the election. So for binary cases, it's very simple. It's 1 or 0. It's one or the other. This is not a binary case. So if the death is not due to cholera, it could be something else. Whatever that something else is will be your null hypothesis. So in this case, an intelligent null hypothesis will be that the death is not due to pump 0, but say it's because more people live in this neighborhood, right? If the population is centered around this region and there is less people living here, and you were to look at the number of deaths, of course, there will be more deaths where more people live in, and the distribution of the number of deaths will be more or less the same per unit number of people living in the neighborhood, right? So that is the alternative hypothesis, that these deaths are not due to these pumps delivering contaminated water, but they could be because more people live in this region. So what we're going to do is to create some statistical assumption that more people live in this area. So we'll put about 65% of the population here and put less of the population in the other places. Then use computer simulation to determine the probability that these deaths could be because more people live in this neighborhood. And that is the null hypothesis, which we'll be using in hypothesis testing. So here you can read this. If the cholera deaths were totally random, then it's unlikely you will have 340 deaths close to pump 0 and so few deaths close to the other pumps. So like I said, we're going to assume more people live around pump 0 and perform a computer simulation. To simplify it, we're going to remove these pumps with too few deaths to be statistically significant. So remove pump 2 and pump 7. You're left with pumps 0, 1, 4, and 5. Then we're going to do computer simulation, which is facilitated using this function. So randomly choose between those 4 pumps for a population size which is equal to the total number of deaths. So 340 plus 65 plus 5, add up all of these, it's about 489. It is 489. So that's the size. Then randomly pick more points closest to 0. At 65% of the data should be close to 0. 15% of the deaths should be close to pump 1. 10% should be close to pump 4. And the last 10% close to 0.5. So this is randomly generated, assuming this is the population distribution. So we call the function with the number of deaths, which is 489, grab the number of deaths closest to each of the pumps we've generated from computer simulation. And the results are shown here. So 323, 81, 46, 39. So there's a lot more deaths here. So this is the null hypothesis again. You're trying to test if this is similar to this. It looks like it's close enough, right? How do you figure out using quantitative measures? So that's where we bring in our concept of confidence interval. So this is just one realization. We're going to generate several realizations and figure out where 340 deaths will lie in the distribution. If it's extreme, then it means the probability that these deaths are because of unevenness in the population distribution is unlikely. And that's what we're moving on to do. So use the same function 1,000 times, actually 10,000 times. That's what we're doing here, using least comprehension, which we discussed before. So store the results in counts and store it in a dictionary. The key of the dictionary is counts. And you will end up having a data frame containing only one column. The column heading will be counts, and the data will be 10,000 realizations of these data set. So we can plot the 10,000 data using the histogram. And this is what it looks like. Let me run it. Okay, so I haven't run a couple here. This works, so you have to run this function first. Run this, then run this. Oh, it takes time because it's 10,000 realizations. So while it's running, we can keep reading what's here. This distribution has been generated under the null hypothesis, meaning the pumps have nothing to do with the cholera outbreak, and the deaths could simply be proportional to the population. Again, that is a null hypothesis. The hypothesis you're trying to test will be inverted, and that's the null hypothesis. So it's very simple for binary problems, like I explained earlier, but for this, you just have to come up with an alternative explanation for the deaths. And here, the assumption is that it is due to population, and that is what we're testing. So this is the result if it's just due to this realization of a population distribution. And now the question is, where does the actual number of deaths, 340, show up in this probabilistic distribution? So how do we figure that out? Percentile of score, which we discussed in topic 6, right? Percentile of score is going to go in there and figure out the area. So this is 340. Figure out the area to the left of this distribution, all of this, divided by the total area, and tell us what that percentile is. It's really high, right? It's very high. Only this small portion is outside of that interval. So it's 97.99, roughly 98%. So the probability, or let's just read out what's here. The high percentile implies that 340 deaths is an extreme value, and you will not expect that from the null hypothesis. The probability that the data lies outside or above 340 is just 2%. And that's what the p-value is 100% minus the percentile that value shows up at. So 2%. P-value is 2%. The lower the p-value, the more confidence you have in the null hypothesis, in the hypothesis. So the way it's interpreted is actually shown here. You will only expect the null hypothesis to be true 2% of the time because the p-value is 2%. The smaller the p-value, the more strongly we can reject the null hypothesis. That's what I was trying to explain. And the cutoff is 5%. There is some debate on that. We're not going to get into it. We're just going to use the p-value of 5%. So if you calculate your p-value like so, and it's less than 5%, then you can reject the null hypothesis. If the p-value is greater than 5%, it means you don't have evidence to reject the null hypothesis. I repeat, if the p-value is greater than 5%, you don't have enough evidence to reject the null hypothesis. It doesn't mean you accept the hypothesis, the original hypothesis. It just means you can't reject the null hypothesis. But if it is lower than 5, you reject the null hypothesis. So in this case, it means we reject the hypothesis that the death is just due to the proportionality in the population. And that means it could be due to the cholera outbreak. So we reject the null hypothesis, but it doesn't mean we accept the hypothesis. It just means we have no reason not to accept it. I think that's the easiest way to explain that. Now, we just talk about how p-values are related to confidence intervals. This is exactly how you calculate the p-values, and it's discussed here. The lower the p-value, the higher the confidence you have in the interval. And that p-value will be lower than 5% to reject the null hypothesis. So, to show the relationship between p-value and confidence intervals, we're going to go back again and look at the example with the poles. So, the hypothetical poles between Ed Orgeron and Nick Saban. This is the data for 1,000 votes, exactly what we had before. This will give you the hypothesis that Nick Saban will win the election. And the null hypothesis will be that he does not win, meaning he either loses or ties the election. And that's explained here. If he loses, then that means Ed Orgeron wins or ties the election. Another way to explain the same thing, that is the null hypothesis. And that will mean that the true Saban win percentage will be 50% or less, right? For him to tie, it will be 50%. For him to lose, his win percentage will be less. So we want to find out whether his winning percentage of 51.1, which we have here, is extreme or not. Where does it fall on the percentile? Do exactly what we did in the previous null hypothesis, right? So doing this. Let me run it and see if that fixes the problem. Yeah, it's not going to run, right? Or is it still running? Let's import first. Good. So it works, and this is the result. I really would like this to get out of the way, but all it does is the plot function. It plots this data frame, and this data frame uses the sample function we created before. No point going all the way back. The sample function takes in the win percentage and the number of samples you want. So we want 1,000 samples. N equals 1,000, but the length of each of the data is 10,000. And we plot up the histogram right here. And we use the percentile of score again, subtract it from 100 so you get the corresponding p-value. And that value is very large. It's 26%. Sorry, 24%. And the cutoff is 5%. So 24% is greater than 5%. So we do not have evidence to reject the null hypothesis. So it's possible that Nick Saban loses because we can't reject the null hypothesis, which is that he loses or ties. And that is written out here in words. P-value is not low enough to reject the null hypothesis that Ed Orgeron will win or tie the election. So what if we do the same thing on the larger poll? So run the larger poll, we load the data set. It's the one that has 10,000 votes in it. And the result indicates Ed Orgeron has a 51.8% chance of winning. So what is the null hypothesis in this case? The null hypothesis in this case is that Ed Orgeron either ties or loses, because the hypothesis is that he wins the election. So different from the smaller sample, because you didn't poll enough people, right? This had Nick Saban winning. So we go through exactly the same thing. Generate 10,000 realizations, plot it up in a histogram, display, in this case, where the true winning percentage will be based on the sample. It's far out here, so you can already tell it's extreme. And if you go ahead and do exactly what we did here, this, you will figure out it's a very small value. I need to go back all the way up to create a new cell, and we can paste it here. So 100, we are trying to calculate the p-value. Dist Orgeron, right? What's the win percentage? 51.81. So what's the corresponding p-value? We expect it to be very low, right? It didn't work because this is not defined, meaning I've not run this, right? So I run this, might take a while, not fast enough. Run this again. PP is not defined. Yeah, I probably imported it as PLT. Yeah, I imported matplotlib as PLT. So that fixes that problem, and this will run now. And it's actually 0.0. There may be another number in maybe the 15th or 17th decimal place, but for all practical purposes, it's almost zero. So we can reject the null hypothesis and conclude that Ed Orgeron will win the election based on the larger poll. And interestingly, we actually won the game against Alabama. And that's the end of today's video. Please feel free to ask any questions. If any of these things are not clear, I wouldn't mind uploading another video, maybe 1 or 2 minutes or 5 minutes, to clarify any common questions you all have.